and it's going to talk about a new lattice-based function and distributed broadcast encryption.
Great. So thanks a lot, Elaine, for inviting me to give a talk. So I'll be telling you today about broadcast encryption and sort of going along the spirit of the workshop side. There'll be some new lattice assumptions here that I'll hope to convince you is worthy of additional study, both in terms of understanding hardness as well as exploring new applications. So the focus of this talk will be the problem of broadcast encryption. So in this setting, there's a number of users. Each user has a secret key. And the goal is the following. I want to encrypt the message to some subset of these users. And the functionality requirement is that all of the users in this broadcast set here should be able to decrypt the ciphertext. While users that are outside the broadcast set should not learn any information about the encrypted message, even if they happen to collude with one another. So we're looking at fully collusion resistant broadcast encryption. And if all I care about were these two properties, there's a trivial construction. Basically, if I want to broadcast to users 1, 3, and 6, I just encrypt the message under each of their respective public keys. So the interesting bit about broadcast encryption is the efficiency requirement, which says that the size of the ciphertext should essentially be the size of the message plus an additive term that grows only with polynomially with the security parameter, and importantly, polylogarithmic with the size of the set. Now, of course, for this to be feasible, the decryption algorithm will need to know which set you're targeting, but the ciphertext itself scales only polylogarithmically with the size of the set. So if you look at this picture, a question that you might ask is, where did these secret keys come from? So I said that each user has their own secret key that they would use to decrypt the candidate ciphertext. And so if we zoom out a little bit, in the picture of broadcast encryption, there's going to be a central authority who holds on to a master secret key. And the central authority is the one responsible for issuing keys to the individual parties. But then this begs the question, what happens if this central authority gets compromised? Right? Broadcast encryption is an example of an advanced encryption scheme. We're augmenting encryption with additional capabilities, but we've also introduced a central point of failure. If you wanted to subvert a system using broadcast encryption, if you just exfiltrate the long-term secret key for the master authority, then immediately you compromise security for all users in the system. This is different from the classic case of traditional public key encryption, where individual users are completely responsible for generating their own public and secret. Okay, so the question then is, can we do broadcast encryption but not have a central authority? And this is the notion called distributed broadcast encryption, introduced by Launay and Zandri in 2014, which is basically, the way that I view it is broadcast encryption, but no long-term secrets anymore. So how does this model work? So just like in vanilla public key encryption, when a user wants to join the system, they just generate their public key and secret key independently of everyone else. There's no central authority. And then what they will do is they will take their public key and just post it on some public bulletin board or a public key directory. So there's just this public key directory that just accumulates all of the individual users' public keys. And then when it comes time to encrypt, what do? I go look at the public bulletin board. And suppose I want to encrypt to users 1, 2, and 3. What I will do is I will look up their public keys, and I will simply run the encryption algorithm. In a distributed broadcast encryption, I will allow for some public parameters. In the constructions that I described, the public parameters will have to be generated by a trusted setup. But this is a one-time trusted setup. It's a reusable setup. Once you do it, there are no long-term secrets after that point. Now, of course, we can also ask for transparent setup and so on. But for the purposes of this talk, I will allow for a one-time trusted sampling of a public parameters or common reference. Okay, so now once you have these public keys, you can encrypt the message to them. And we impose the same efficiency requirements exactly as before. The size of the ciphertext should be the size of the message plus something that grows only polylogarithmically, or more generally, you can also ask for sublinear in a number of users. When I decrypt, what information do I need? Here in the decryption algorithm, I allow it to take all of the public keys for the honest user. So you assume that the public keys are known at decryption time in order to actually recover the actual.
So David, comparable to broadcast encryption, right? I mean, on the one hand, you don't have a trusted authority. On the other hand, the encryption algorithm needs to know all the public keys.
Good. Exactly. But this does not imply broadcast out of the box, because indeed the decryption algorithm now needs some information about each individual public key. Although you do get a version of centralized broadcast, you can imagine that if you have a bounded number of users, the individual public keys for the individual users could just be part of the public parameters of the broadcast encryption scheme.
Right.
why does the decryption need to know all of S, the public key in all of S? It's not possible if it doesn't.
If it doesn't know the set itself, it's not possible. It is in principle possible to only need decryption to take as input the public parameters, some aggregate information of all of the public keys, and only the set S. So that would be a stronger requirement. We don't know how to achieve that, at least from simple assumptions. From obfuscation, I think we can do it. Yeah, so you need some information about S. Here, I'm going to allow the decryption algorithm to take the public keys that we're targeting as part of the input.
Possible to do something like, like this guard playing type thing where you have like a hash of the public keys.
Yes. So I think with obfuscation, you can do that. Yes. So from LWE, I don't know. Yeah. So the Dublin guard approach works for IDE. So if I'm encrypting to a singleton set, if I have even 2 users, I actually don't know how to do it anymore. Yeah. Okay. Great. So so as pointed out, decryption does require knowledge of the public keys in the broadcast set. Okay. And the security requirement is that users that are outside the set should learn nothing about the message, even if they happen to be. So exactly the same security requirement as in centralized broadcast encryption. So what do we know about the feasibility of this notion? So in the same work where Bonnet and Zambri introduced it, they showed how to build distributed broadcast encryption from indistinguishability obfuscation together with one-way functions. More recently, we can show how to build this from witness encryption and leveled homomorphic encryption. And we can also actually, turns out, to build this from something called registered attribute-based encryption, which admits a number of pairing-based instantiations. And very recently, in the last year, we also have explicit pairing-based constructions of distributed broadcast encryption exactly. I'll mention that the pairing-based constructions that I mentioned here, both of these only support an upwardly bounded number of users, whereas the constructions from more heavyweight tools like I/O or witness encryption actually support an unbounded number of users. So something that you might wonder then is, what do we know from lattice constructions? Okay? So that's going to be the focus of this talk. We're going to focus on lattice-based constructions of distributed broadcasts. And before I tell you what's known about lattice-based distributed broadcasts, let me step back a moment and first tell you about lattice-based centralized broadcasts. So centralized broadcast encryption from lattices has been one of the major open problems in the field. I think it's one of the things that we have very nice constructions from bilinear maps. And yet still today, we do not have constructions from the plain LWE assumption. It still remains a major open problem. And I encourage all of you to spend some time thinking about it. It's a really beautiful problem. It's a very simple functionality, and yet still has eluded all of our efforts as a community for essentially more than a decade. So nonetheless, we have made quite a bit of progress. So Svika and Vinod, in 22, they proposed a lattice-based instantiation of centralized broadcast encryption. This is a very elegant construction. Unfortunately, it doesn't have an explicit assumption. It doesn't have a hardness assumption. But there's no attacks at the same time. So it's an explicit candidate. There are no attacks, but also no security rules. Hotek, in subsequent work, showed that from this evasive LWE, so this was the same work that introduced this evasive LWE assumption, he gave the first example of an optimal broadcast encryption from lattices with an explicit hardness reduction to the evasive LWE assumption. I'll say a little bit more about the evasive LWE. This is the same assumption that Rachel mentioned at the end of her previous talk. But essentially, this is a new non-falsifiable assumption. And very recently in crypto, this past crypto, Hotek showed how to construct broadcast encryption from the succinct LWE assumption. This is the assumption that I'll be focusing on in this talk. So I'll tell you about this assumption very shortly. And I'll mention that while I say that these constructions give centralized broadcast, they actually give a little bit more than that. They actually build something much more general, which is a succinct ciphertext policy attribute-based encryption. Broadcast encryption is just a special case of this more general. Okay, so quite a few things are known about broadcast encryption from lattices, albeit from non-standard assumptions. If we turn to distributed broadcast encryption, essentially the only current lattice instantiation goes through the heavy machinery of witness encryption. And we do technically have witness encryption from lattice assumptions, but this requires an even stronger version of the evasive LWE assumption, something called the private point evasive LWE, which is a stronger version than needed for a centralized broadcast. And in fact, we have counterexamples for the most general form of private point evasive LWE. Of course, the ones that suffice for witness encryption, as far as we know, are still plausible. Right, but this is sort of the lay of the land until now. So in this work, we show how to build a distributed broadcast encryption from the succinct LWE assumption.
What's the efficiency requirement to get that?
Same as the centralized one. Yeah. So the size of the ciphertext should be sublinear, and in this case, will require polylogarithmic in the size of the broadcast. Yep. Okay. So let me tell you about this assumption. So I am a big fan of this assumption, so I encourage you that I want to convince you that this is something worth looking at further. So the L succinct LWE assumption asserts the following. So it says that the standard LWE assumption, so here's the standard LWE assumption. It says that if I give you a matrix A and a noisy linear combination of the rows of A, that looks pseudo-random. That's unique. So the L-succinct LWE assumption says the following. LWE is hard, but still with respect to this matrix A, but I give you some additional hint. I give you a trapdoor for a matrix that is related to A. And what is this trapdoor? Well, it's this matrix D here, which basically contains the blocks of A along a diagonal. And then I'm going to adjoin to it a very tall and very narrow matrix. So a randomly sampled matrix, very tall, so has dimension L times N. And the width is very narrow. It's M. M is N log Q. I forgot to write that, but M you can think about as roughly order N log Q. So I give you a matrix, which is A along a diagonal, and then I join to it a very tall, very narrow matrix. I give you a random trapdoor for this matrix. Okay, so here, this is the gadget matrix. This is the powers of 2 matrix that we saw in the previous slide. And the L-succinct LWE assumption basically just says that LWE still holds, even though I give you these random matrices and this trapdoor. Okay, so I'll try to give you a little bit of intuition for why this assumption is useful during this. So the first thing I want to note is that this is a falsifiable assumption, right? This is a distinguishing assumption. No, so unlike evasive LWE, this is now a falsifiable.
So for L equals 1, this
is that's the next slide. Yep. So let me say a little bit about what is known about this assumption. So as the node already pointed out, the L equals 1 case is implied directly by LWE, just by standard trapdoor extension techniques, right? So the L equals 1 case basically says LWE is hard with respect to the matrix A, given a trapdoor for A concatenated with random matrix. If the random matrix is wide enough, then by standard trapdoor extension techniques, you can actually simulate, right? So that follows by LWE. The other case that follows by LWE is that I make this matrix U here, this thing right here, very, very wide. So here it would be N times L times N log Q, or L times M. Then again, this follows from standard LWE, again, by standard lattice delegation or trapdoor extension. Okay, so these are two settings where we do have hardness from LWE. Unfortunately, though, for the applications, we typically require large L. So L here in our application will be the number of users, roughly speaking. In an application of broadcast encryption or full-text construction of ciphertext policy ABE, L is like the attribute length. So this is going to be larger than 1. And moreover, all of these constructions require that U to be very narrow. And it turns out that the width of U is basically what gives us the power, the succinctness. So the wider we make U, the larger the ciphertext becomes. And this eventually becomes uninteresting if U is allowed to scale linearly with L. So so the fact that U is very narrow is what's giving us power in this assumption. This is what gives us compression. Yeah, question?
Is this the same assumption that implies functional commitments?
Yes, so I'll say a little bit about that shortly. Yeah. So this assumption is good enough for functional commitments. The SIS version of this assumption is good enough. Yeah. So before I go there, so this is a falsifiable assumption.
Is there any regime which is broken? Like
L equals 0 is broken. Sorry, not L equals 0. When U is 0, when the width of U is 0, it's completely broken, and then you're just giving out a trapdoor for A.
Even if you're like,
but U, I think if U is constant, so it's broken. Yeah, if U is constant, it's broken. And I think if U is super logarithmic, then we already don't know. Yeah. Good. So this is a falsifiable assumption. It's also instance independent, which I think is appealing from a constructions perspective, because compared to, let's say, a proof from evasive LWE, right? Because you could always say that, well, if I'm proving something from evasive LWE, so if you recall, I guess I didn't introduce evasive LWE here, but if you recall in evasive LWE, the assumption is usually phrased as if some precondition holds, then some pair of distributions are indistinguishable, right? So you can say, well, why not just make the post-condition for evasive LWE my falsifiable assumption, right? The post-condition is a falsifiable statement. It's arguing that 2 distributions are indistinguishable. But if you look at the security proof to evasive LWE, it's not going to be the same. The post condition actually depends on the adversary, right? We always define the sampler. The sampler algorithm depends on how the adversary behaves. It might depend on the key queries that the adversary makes in the security game. And so you can't write down a single assumption under which you can then prove security, right? So the fact that this is an instance-independent assumption basically is more robust in some sense. Like I don't need to tailor my assumption to the particular construction or to the particular adversary.
Do you care about the distribution of U or sort of like any distribution of U for which?
Good question. I think for the constructions, we don't care about the distribution of U.
Okay.
Yeah,
Okay.
yeah.
Okay.
Yeah, so I think uniform is sort of the least structured, right? So sometimes if you have a structured view, you can get better efficiency properties.
Mm-hmm.
Yeah, so for one of the applications I'll describe this functional commitment scheme. If you have structured view, I think you can shave off a loss factor in efficiency. Yeah, but certainly I think from a functionality standpoint, if you can prove that this assumption holds for some distribution of U, I think we would be in business. Yeah, good. So one more thing that I think, one more appealing property of this assumption is that if you like evasive LWE, this is indeed implied by evasive LWE plus LWE. So I'll leave that as an exercise. It's not too hard to show that evasive LWE, if you believe public point evasive LWE and plain LWE, this assumption holds. And sort of the usefulness or the power of this assumption really comes from the fact that this trapdoor has a U that is not too wide, and that turned out to be very useful for compression. So Hotek's work showed how to use it to get CPAVE with short ciphertext, in particular, is applied broadcast encryption. And in an earlier work that Juan alluded to, we showed how to use this to get functional consent for circuits from the SIS version of this. Okay, all right. So let me tell you a new application to distributed broadcast encryption. And the starting point is I'm actually going to build a centralized broadcast encryption, and then I'm going to show how to do distributed key generation. And one of the interesting things or interesting properties of this broadcast encryption that I'm going to tell you about is that I'm not going to start by building a ciphertext policy ADE scheme. I'm actually going to take a much lower tech approach, which is closer, I think, in spirit to some of the very classic pairing-based broadcast encryption schemes back about 20 years ago. So this goes back to the BGW broadcast encryption from pairing. So there's not going to be any homomorphic encryption machinery used in our construction. So let's see what it looks like. So in our centralized broadcast encryption, each user will have a public parameters associated with it. So this will be a matrix WI and a vector RI. So you can think about RI as a random short Gaussian vector. Okay? So every user has a matrix W and a vector R. And then there will be some common public parameters that are shared across the scheme, which is the matrices A, B, and a vector P. Okay? So that's it. This is all of the public parameters we'll need for the construction. So let's see what the ciphertext looks like. So this will be a classic dual regev encryption. So if you ignore the second part, then this is really just dual regev, right? I take an LWE instance with respect to A, LWE instance with respect to P, and in classic dual regev, your secret key would be something that recodes from A to P, right? It would be a short R such that A times R equals P. So here we want some more functionality, right? We want to have to support this broadcast functionality. We're going to introduce some additional components. So the additional component is I'm going to give out an LWE sample with respect to the matrix B plus the sum of the public keys for the users in my set, right? So every user in a set has a matrix associated with them. I'll sum them up, I'll add it to B, and I'll give it LWE sample with respect to. So the question then is, how do we get correctness, right? So I'm going to focus on correctness first. So first, let's recall the requirement. We want that every user who is in the broadcast set should be able to decrypt the ciphertext. Okay, so they should be able to essentially recover S times P. If they can recover S times P, then they can recover P. So that's what we're going to do. And the way that we're going to do it is we're going to give them some decryption key, right? What does the decryption key look like? So in dual regev, I would just give out the decryption key that goes from A to P. Here I need to give out something that doesn't quite go from A to P. It goes to A to P plus some additional junk, right? Some additional terms that tie it to that particular user, that ties things to the user I. So I'm going to recode not to P, but to P plus B times RI plus WI times RI. So notice that W times RI, WI RI is sort of the public key for that particular user, and then RI is the component that will be useful shortly. Okay. All right. Good. So let me show you how we can decrypt using this setup. So we have a key that basically recodes from A to the sum. So, and I have an LWE sample with respect to A. So the first thing that I can do is I can simply multiply S times A times the secret key. So now this gives me S times P plus this additional components that depend on user I. So we have made a little bit of progress because we got this S times P. S times P is what we ultimately want to recover the message. So the question is, how do we get rid of these additional terms? Well, the second thing that I can do is I can observe that I can get the B times Ri plus the Wi Ri term from the second component here, right? By simply multiplying the second ciphertext component by Ri, right? If I multiply an Ri, then I get S times Bri plus the sum that contains Wi Ri. So here I'm going to use the fact that if I is in the set, then Wi is part of the sum. So this term right here that I want to eliminate is actually contained in this summation. Okay? And at this step, we will require that the Ri's are sufficiently short. So now let's just simply compute the difference of these two terms. If I subtract them, then I get the blinding factor that I care about, minus the secret times what I will call these cross terms, the product of the J's public key with user I. So if you're familiar with the pairing-based constructions, at this point, how do we, this would be something like G to the alpha J times beta I, where alpha J is sort of the J's users component, and beta I might be the ith users component in the ciphertext, right? And how do we decrypt in the pairing-based world? Well, we simply gave out G to the cross terms as part of the public parameters, right? So many of the previous pairing-based constructions have that kind of structure. So what is the analog in the LWE world? We need some way of getting rid of these cross terms. Well, I'll just simply publish pre-images in the public parameters. So I'll just give out A inverse of Wi Rj for all I not equal J. So now, if I give you S times A and I give you A inverse of Wi Rj, notice that you can compute the secret times Wi Rj for all I not equal J. So this gives you a way to eliminate all cross terms, and then you need to have your secret key to get rid of the non-cross term in order to do it. And this actually completes the process. So I subtract these two things, and then I subtract out the components from the public key, these cross terms, and that will allow me to exactly recover the blinding factor. Okay? So this gives us a centralized broadcast encryption. I'm not going to prove security. I actually don't know how to prove security of this particular construction, except from evasive LWE. So using evasive LWE, I can prove security. I don't know how to reduce the L6 LWE as written. I have to do a little bit more work to get the reduction to L6 LWE. But from a functionality perspective, this is already gives you a broadcast encryption. Okay, so the reason that this is centralized is because in order to sample these cross terms, right, you have to give out these pre-images under A of these cross terms. And we also have to sample these secret keys, which again are pre-images under A, right? So the way that we compute these right now would require knowledge, or seemingly require knowledge of a trapdoor, right? So the master secret key for this construction would be the trapdoor for A, and then using the master secret key, you can generate the cross terms and the secret key. Okay.
So David, once again, so
yeah.
the WIs are random matrices.
Random matrices, yes.
Okay, so the issue is somehow WI comes up many times.
It comes up many times, exactly. Exactly. So there are too many, basically the number of users is much bigger than security parameter. Yeah. So it's not easy. It's not clear how to sample this in that direction. Yep. So we'll talk about that next slide. So let's talk about the challenges for distributing this up, right? So I don't want anyone to know a trapdoor for A, right? So I want this construction, but now there's no trapdoors because I want to distribute a broadcast encryption where there are no long-term secrets, right? So nobody should know a trapdoor for A. And yet I still need a way to generate these decryption components. So the approach that we're going to take is we're going to follow the template from our centralized broadcast encryption, where each user is going to pick their own WIs. The RIs will be part of the public parameters. I'm going to split up the public key. So before it was WI and RI was the public components for user I. Here I'm going to say, I'll let the user pick W, and I'll put the R as part of the public parameters. So there'll be a one-time setup that generates the Rs. Okay, so in our public parameters will just be the matrices as before, and then these RIs. Each individual user will pick WI. Okay, so I can do this. So the question is, can I get correctness, right? So let's just worry about functionality. So in order to decrypt, we need two properties. We need to be able to generate cross terms, and we need to be able to generate secret keys. So we need to find short pre-images, Yij, such that A times Y equals Wi times Rj, And we also need to be able to find secret keys where a times YII is equal to the non-cross term plus this additional, right? And the question is, how do we do this without a trapdoor for A, right? So you can think, I think as Steve Note alluded to, why not just sample a bunch of YIJs myself and then hope that there's a WI that is consistent. So the issue is that this is an over-constrained linear system. You will not be able to do this without essentially solving SIS. Yeah, so this seems like a computationally hard problem to sample these pre-images that satisfy this relation. Okay, so let me consider a simpler problem. I'm going to simplify things slightly. Suppose I don't care about these extra things. I just want to solve the problem of sample WI together with short YIJ, such that AYIJ equals WI. Okay, so ignore the fact that for the secret key, I technically need something more. Let's just try to solve this simpler problem. This really captures the essence of the problem. I want a bunch of these correlated pre-images that is consistent with a single W1. Okay, any questions?
So what if you pick a sort of short matrix, small entries matrix R, such that A times R equals WI?
Okay.
And then sort of, you know, the YIJs are linear combinations of.
Yes, so I think you end up with a problem in security proof. So yeah, it will not have the right distribution. Yeah, so that would solve the functionality issue, right, but we wouldn't know how to prove security. Yeah, but that's on the right track to the solution I'll be describing. So here's what we're going to do. So the problem we want is some mechanism for sampling these short pre-images that are all targeting these correlated values, right? I want to sample a single WI and then an RJ that I don't have control over. Right? So the public parameters right now has A, B, and the Rs. What I'm going to do is I'm essentially going to include in the public parameters a bunch of pre-sampled public keys. Okay? So the pre-sampled public keys will just be a bunch of random matrices Z and a bunch of short pre-images of Z I times RJ. Okay? So I'm just going to do this. And the way that I'm going to construct my WI is I'm going to take a random subset sum of these ZIs. And then my pre-image will now just be a random subset sum of the pre-images that I gave out. Now, again, there's still the question about, well, is this the right distribution? How do we argue security? But at least from a functionality standpoint, again, we have something that works. And this is very close to, I think, your proposal.
So the marginal distribution of WI is this random?
Yes, the marginal distribution will be WI, will be uniformly random, assuming that there's enough Z's.
Right.
Yeah, so Z is basically bigger than N times M times 1, 2. Yes, the marginal distribution of WI will be uniformly random. You do have to worry about the distribution of the pre-images that you give out. Okay, but at least this gives us a way to sample these public keys in a distributed manner. So we just publish a bunch of pre-sampled things, and then we take short linear combinations of them. I'm going to actually offer a more general view of this problem that will actually lend itself very nicely to the security proof, so that we don't have to reason about distributions. And the more general view of it is, I'm just going to write everything as a linear system. I'm just going to rewrite my goal, this sample AYIJ equals WIRJ. It's basically sampling a solution to this linear system, right? So if you view this linear system, basically, if you read off each block or each row of this system, I basically get A times YIJ is equal to some linear combination of the Z's times RJ. And what I'm going to do is I'm going to just say, well, this linear combination of the Z's, I'll just call that my WI. And so a solution to this linear system now is exactly a solution that satisfies my original goal. Okay, any questions about this? So again, I haven't done anything fancy. I've just taken the original thing I described and just wrote it as a matrix. Okay, so I'm going to write things a little bit more compactly. Hopefully, you'll see the reasons shortly. I just put all of these together. So nothing fancy going on here. And then basically Z1 times R1 of the ZK times R1, so on. You can just write as a okay, and the problem now is basically I want to sample YIJs and a D such that this linear system. I want to sample a solution to this linear system. And once I have done so, the public key that I get out, this WI, will just be a linear combination of this. Okay, so any questions about this? Again, this was just a reformulation of the problem as finding a solution to a suitably defined linear system. So the last thing I'm going to do is Now I want to sample solutions to this linear system. And if I don't want to think about distributions, well, let's just say that I want to sample a Gaussian distributed solution to this linear system. How do I do that? Well, I publish a trapdoor for this matrix A in the public parameters. So this completes the construction of the scheme. Basically, the public parameters will contain this matrix A, these sort of pre-sampled public keys, together with a trapdoor for this particular matrix. And now it is very easy to sample a solution to this linear system. You just use the trapdoor to solve SIS. Yeah, and then you can actually argue, in fact, that the marginal distributions of the WIs is uniform random, and then these YIJs are basically random Gaussian solutions to this system. Yeah, so as long as their parameters are set properly.
These matrices on the right, they're not uniformly random, clearly, right? I mean,
these matrices, no, these are not. Yes, good. So if I want to do a reduction, then I was like thinking that so something has to happen.
Right. Good.
Yeah. Good. Yeah, so I'll address that shortly. Okay, and now, as I mentioned before, we had this simplified problem where we didn't worry about what we were targeting. We were just targeting WIRI. But if I write everything as a sampling solutions to a linear system, notice that I can target WIRI plus whatever I want. I just insert the offset into the corresponding row, and again, use this trapdoor to sample a solution to this linear system. Okay, good. And so this gives me a way to do distributed key generation. Any questions about this? Okay, all right. So how much time do I have left? Did I do it? Okay, I can try to do the proof. So I can actually show you how to prove security. So proving security is actually quite simple. So first, I'm going to cheat a little bit. I'm going to prove security assuming LWE is hard given a trapdoor for this matrix. Yeah, and, I'm cheating a little bit that I constructed this matrix because I wanted a particular scheme to be secure. It turns out that if you have an succinct LWE trapdoor, you can simulate a trapdoor for this matrix. So this is how we're eventually going to get the reduction to succinct LWE. So the intermediate step is I'm going to assume that LWE is hard, even if I give you a trapdoor for this particular matrix. So let me show you how the proof goes. So we're going to focus on selective security. So in a selective security game, the adversary is going to commit to the challenge set S at the beginning. And then the challenger is simply going to send over the public keys as well as the challenge ciphertext. So here I'm just going to consider the special case of encrypting 0 or 1. So the adversary doesn't have the special. So what is the goal in a security reduction? Our task is, given the LWE challenge, right, either SA or random, together with this trapdoor, simulate the challenge ciphertext and simulate all of the public keys that the adversary, that the challenger uses together. So let's take a look at how we do that. So this is actually fairly straightforward now. This is a standard partition. So let's see how it goes. So first, the public parameters can actually be simulated honestly. We have a trapdoor for this matrix here. The honest scheme is just using this trapdoor to generate public keys. We can do exactly the same. So we can simulate the public keys just using the honest algorithm. So what we are left with is how do we simulate the ciphertext? So I am cheating somewhere, so try to catch me. So there's something wrong with what I'm saying, but I'll fix it at the very end. Okay, so let me go jump to simulating the ciphertext. So how do I compute S times P? Well, I'll just set P to be A times something short. If I do that, then notice that I can just simulate it using the challenge. Okay, so that's all okay. How am I going to simulate S times B plus this sum? So this is a little bit annoying, right? Because all we have is S times A. So we want to express this whole thing as A times something short that we control in the reduction. So what we're going to do is we're going to program the set. So here we're going to really rely on the fact that we're looking at selective security. So the adversary tells us which set it is. I'm going to program B to be A times R minus the sum of the public keys for the users that appear in the set. So suppose I do that. Then the second ciphertext component will just be S times A times R, which we can now simulate from the challenge. Okay, and now notice that everything can be simulated directly from the challenge. So there is one problem. Does anyone see what the problem is? So there's one problem with this programming step. So how do we program? We program B to be something minus the public keys. But how do we choose the public keys? Well, the public keys were chosen as pre-images of this particular matrix. Notice that this matrix depends on B. It's like, which one are you going to pick first? Are you going to pick B first, or are you going to pick the public keys first? right? They're sort of correlated. And in some sense, what I'm telling you is way too good to be true because I'm generating the public keys honestly. That means my reduction algorithm has the secret keys for all the users. So what's the point of the reduction algorithm, right? So somehow we have to break this circularity. We have this interdependence where B depends on the public parameters and the public keys depend on B. We have to choose one of them first. But there's one more fact that we haven't exploited, which is, do we have to give out this component? This component is a secret key for the particular user. This would never actually be given to the adversary in the real scheme. So what we can do is, instead of targeting P plus B times Ri, I can just switch the targeting to 0 in this particular component. And just by analyzing the distribution, so here's where we're going to analyze the fact that this is a Gaussian distribution, the marginal distributions of all the other things actually do not change if I'm only changing the target for the ith component. If I don't have to give out the ith pre-image, then the marginal distributions of all the other keys and B actually doesn't change. And now, notice that the public keys no longer depend on B. So I can simulate the public keys first, and then I can program to complete the selective security. Okay. Great. So again, so this is the place where the fact that we're looking at Gaussian pre-images come in handy. And we can sort of reprogram what we're targeting without actually changing the view of the adversary. So this is statistically indistinguishable from what the adversary would see in the real scheme.
I see. So you can statistically simulate public keys for I not in S together with the secret keys.
Yes.
And the public keys for
exactly. That's right. Yep. That's exactly right. Yes. So of course we have to set the parameters that the Gaussian is decomposed properly, but yeah. Well, once you do that, you can statistically simulate. Okay, great. Okay, so the one remaining caveat is the one that the node pointed out, which is I kind of cheated here, right? I told you about this L-succinct LWE problem, but the trapdoor I'm giving you is not the L-succinct LWE trapdoor. In particular, this matrix here is very far from uniform, right? This is a very structured matrix, very correlated. Here, I'm going to just tell you to trust me that there's basically given a trapdoor for the L-succinct LWE problem, I can generically transform it into a trapdoor. For this particular problem, there is some loss in the dimension. So we want L dimensions here. Then we need to start with an L-succinct LWE trapdoor where L prime is bigger than L times some poly. So L times M. So, yeah, so I'll refer to the paper for that. But essentially, if you write out what the pre-images look like for these two trapdoors, they're very closely related. Yeah, essentially, you can view that this is actually like the transpose. Yeah, so I'm happy to discuss that more. Okay, so just to summarize, here I've described a construction of distributed broadcast encryption for L users, where the public parameters are quadratic in the number of users. Each individual user's public key is linear in the number of users, but the ciphertext size is only depends polylogarithmically on the size of the set. And I think there's a number of interesting open problems that I'll leave you with. So one is, can we get shorter CRS? Can we get short public keys? So here we have this dependence on a total number of users. Ideally, we'll have a short CRS or short public keys. Can we get something with a transparent setup? So where the public parameters can be a random string rather than a structured string. We don't know how to do that. So we know how to do this from witness encryption or obfuscation, but neither from pairings nor lattices functions today. Can we try to do security from plain LWE? I think this is the big open question for even just getting centralized broadcast encryption. Trying to do something from plain LWE, I think would be a major step forward. So this, I think, is a beautiful open problem. And I think as we're sort of proposing and studying these new kinds of lattice assumptions, I invite cryptanalysis of these new assumptions, especially as we show more and more applications can be built on some of these new assumptions. Can you give any better attack? So I think right now the best attack on L-succinct LWE is basically just ignore the trapdoor, ignore the hint, and just solve LWE. So is there some non-trivial way of exploiting that trapdoor to actually analyze the L-succinct LWE? And with that, I'll conclude. Thanks.
What's the best parameters for if you use aggressive variance of LWE?
So I think for right now, I would conjecture that you can do L-succinct LWE. Just take existing parameters for LWE, and then for any L, it's fine.
No, I mean L and L square.
So instead of L-succinct, if you assume evasive LWE, do you get?
Oh, I think you assume evasive LWE. I actually don't know about constructed. I guess better parameters using evasive LWE. Yeah, I haven't thought about it too carefully.
one question, if I may. So do we know instruction of regular broadcast encryption from succinct LWE?
So this one will give it that.
Oh, I see.
Yes, with long public parameters. So the public parameters will.
Yeah, what I meant was short public parameters.
Ah, with short public parameters. Centralized
Which is something that you can get from LWE plus bilinear, generic bilinear maps, right?
Ah, I see. So no, we don't have optimal broadcast from L6 into LWE.
Okay.
Yeah.
And that is something that Holtec gets from.
The Holtec gets yes, the Holtec gets it from evasive LWE, gets optimal broadcast.
Optimal.
Yes.
That's what I
right.
Replicated with
I see. So with L6 into LWE, Holtec construction also has long public